and we will discuss the estimation method, which is called ordinary least squares. So let me remind you why are we doing this. So in the last lecture we introduced something which is called the linear regression model. The idea is to decompose the variable of interest y into the part which depends on x and which linearly depends on x, and some part which is unrelated to x. You can see some similarity to the model that we have discussed during our 2 lectures in statistics about ANOVA. But in ANOVA, the problem was that we didn't have the quantitative variable here. So x is number. In ANOVA, we had some factor of different levels. But again, there is some similarity between these 2 models. And ANOVA is also a linear model. So this model represents the outcome variable y as a sum of 2 parts. So one is the conditional expectation of y given x here, and another part is the error term, which represents the effect of factors other than x, because, well, we cannot believe that only x affects y. There are some other factors as well. And I hope you remember our example used in the previous lecture. So we spoke about test scores as the outcome variable, and one of the possible factors that can affect the test score is the class size, measured as a student to teacher ratio on the place of x. Well, definitely we have discussed that the class size is not the only factor affecting the student to teacher, affecting the test score. So that's why we introduce this error term, the effect of other factors. Well, we can think of this conditional expectation as the mean or average value of yi for the known value of xi. And we also discussed this. If we know x, then we are able to calculate some mean or expected value of y for this level of x. And in this model, we have 2 population parameters, the intercept beta 0 and the slope beta 1. And the problem is that these population parameters are unknown. Well, beta 1 represents the difference in y associated with the unit difference in x. And this is what we are interested in. We want to understand how the change in x can influence y. What is the strength of this relationship, let's say. Well, these parameters are unknown, and we have studied in statistics that once some parameters of the population are not known, we must collect the data, and based on the random sample, we must estimate these unknown parameters. And that's what we are going to do today. Before discussing the estimation method, we will make some revision from statistics, from probability theory, just to understand what we are doing. So here was this problem graphically. You have the points of the data, 420 points, and you want to find out the line which fits better this data. That's the problem that we are gonna do. So first of all, let's repeat some theory about estimators, just to remember what exactly we are doing. So what is an estimator? It's a particular type of a statistic, which is the function of a sample. So we collect a sample. Based on this sample, we calculate something And the rule how we do this calculation is called an estimator. And we are using these estimators all the time in statistics. So an estimator tells how to calculate the value of an estimate. So estimate is a value, is a number. It's one particular outcome of this estimation procedure based on the measurements contained in the sample. When we draw a sample, the realization of this estimator is called the estimate of theta. And every estimator, please remember, we are talking about this all the time in statistics. Every estimator is a random variable. And at this moment, we know two types of estimators: method of moments estimators and maximum likelihood estimators. So I hope you somehow remember that those two methods or those two types of estimators are derived based on different methods, right? So for the method of moments, we wanted to know the moments, the population and sample moments of the random variables of interest. We equated them, and then we derived the estimators. For maximum likelihood, we build the likelihood function. We maximize this likelihood function with respect to the unknown parameter, and that's how we calculate the estimator, how we build the estimator. And there are several properties of estimators that we also have discussed. The estimators must be unbiased. And this property in the course of econometrics is one of the most important. We will be talking about this unbiasedness starting from lecture 5 at least, and then all the time. Consistency. So yeah, by the way, what is unbiasedness? Unbiasedness means that this random variable estimator must have an expectation which coincides with the true population parameter of this coefficient, or of this parameter. Consistency. Consistency is something different. It means that once you collect a large sample and in probability your estimator will go to the true population parameter. If you increase the sample, the probability of deviation of your result from the true value shrinks to 0. And efficiency. Efficiency means that the variance of this random variable theta hat must be the minimum possible out of all other estimators. So this is what we need to remember about estimators for today's lecture. Next, let me remind you something from algebra that we did on probability course. We know that there is a population variance, and population variance is the expectation of the squared deviation of x random variable from its expectation. We also proved in probability that another way how we can calculate population variance is this. So we calculate the expected value of x squared minus the squared of the expectation of x. We use this many times. I hope you remember this. We can transform this formula. I'm not gonna derive, but I hope you will believe me that we can transform this into the sample variance. So we know that the sample variance is calculated in this way, right? It's something that is known for us. But we also can transform this formula into these two parts. So instead of expectation of x squared, we are using this sum of x squared. So this is based on sample, right? So we take every x on the sample, square this, sum over them, and then divide by n minus 1 because it's sample variance, right? And what is the sample counterpart of expectation of x? It's x bar, but once you calculate x bar, you divide this by n. So that's why you need to multiply this back by n and then divide by n minus 1 and then square this. So that's what happens here. So the population covariance is another measure that must be familiar to us from probability course. So covariance is something similar to variance, but instead of one variable, we have two variables, x and y. And so here we have the product of these deviations of x and expected value of x and y and expected value of y. And similarly to this formula, we can extract, or we can reformulate this as the following thing. So that's expectation of xy minus expectation of x multiplied by expectation of y. And now we also want to transform this into the sample analog. So the sample covariance, we haven't discussed this in statistics, but it's fully similar to the sample variance. So sample covariance is this expression. So instead of xi minus x bar, you have xi minus x bar, yi minus y bar, sum over all of them, and then divide by n minus 1. And the same idea here. You can represent this formula in the following way, and get the same result. So we will need these for some derivations today. Okay, so that was the repetition, and now let's go to the essential part. Let's discuss about the new method of estimation. So you will know three methods now: method of moments, method of maximum likelihood, and finally there is going to be ordinary least squares estimation. So what is the idea of this method? So the OLS estimator chooses the regression coefficients so that the estimated regression line is as close as possible to observed data. I guess it's logical, right? So you want to find such parameters beta 0 and beta 1 that will give a line which fits the data as much as it can, or it is as close as possible to the observed data. How do we measure this closeness? So we measure this by the sum of squared mistakes when we make a prediction of y given x. So mathematically, how we can do this? If we have some estimators of beta 0 and beta 1, just any estimator, so just some guess about value of beta 0 and beta 1, we represent this guess as b1 and b0 and b1 with Latin letters. So those are just some numbers, b0, b1, our guess about the unknown population parameters. The regression line, which is going to be based on these estimators, is here, b0 plus b1x. So that's a regression line when we put into the linear regression these two numbers, b0 and b1, which are our guesses. And that's exactly this regression line, b0 and b1, exactly represents what you have seen here. So these 1, 2, 3, 5, 10 lines, they all have different b0 and b1, different values of these two estimates. So now, out of these multiple possibilities, so the predicted value of y is going to be also this. And now the error, the mistake. The mistake is going to be this difference, yi, so the observed value of y, minus the prediction. So we have discussed this error term, but this is a mistake. Now this is something different. So basically going back to the graph that I showed you, so what we are talking about. So let's take this point. this point up here. This is the so the vertical coordinate of this point, 700 something, right? This is the observed value of y. This is what we have in the data. Now the vertical distance from this point to each of these lines represents the mistake. Look, for example, the mistake for this blue line is the smallest. The mistake for this yellow line is the largest, right? Because the distance, the vertical distance between this point and the line is the maximum here. But on the other hand, we can take, for example, this point here. So the vertical coordinate of this point is, well, 600, let's say 55, something around. And now look, the vertical distance, the error, the mistake for this point from the yellow line is the smallest, and from the blue line is the largest, right? So it's not like you have for all points the smallest mistakes for only one line. So for some points you will have the smallest mistake for blue line. For some points for the yellow line there are going to be the smallest mistake. But that's the idea of this mistake, right? So the mistake is calculated as the actual value of y minus what we can predict, what lies on this on this straight line, the distance between these two. Or we can open these brackets and we will get this. This is going to be the mistake. Now, what is our task? Well, we calculate the sum of squared mistakes. Why do we want to square them? Because we want to make all these mistakes, doesn't matter whether they are positive or negative, to be positive mistakes. This is something similar to the way why do we calculate variance, having squared deviations. So, and then we sum over all these squared mistakes. So we calculate the sum of all of these mistakes. And this is the measure of closeness. So for every line, for every possible line that we can draw inside that cloud, inside that scatter plot, we must be able to calculate this sum for different numbers of B0 and B1, for different values of B0 and B1. And now, what is our task? We want to make it as close as possible to the observed data. So what does this mean? It means that we want to minimize this sum of squared mistakes. And the rules how to calculate B0 and B1 such that they minimize this sum of squared mistakes are gonna be OLS estimators for beta 0 and beta 1. I guess the idea is very simple. Once again, we want to find such values of these two unknown parameters, beta 0 and beta 1, based on the sample, such that the squared mistake, when we are predicting the value of y, the squared mistake is the sum of squared mistakes is going to be the lowest possible. Our error is the lowest possible. And this is something similar to the likelihood method. In that method, we maximize the likelihood to observe the sample. Now we want to minimize our error while predicting value of y. So now there is going to be a little bit of mathematics. How do we do this minimization procedure? Well, our goal is to solve the following minimization problem. We take the sum of squared errors or sum of squared mistakes. And we want to minimize this expression with respect to b0 and b1. So we want to find such b0 and b1 that minimize this expression. So what is the first step when we do the minimization problem? Who can help? What?
We derive it, make it derivative, huh?
We take derivatives, of course. We take this function and we take derivatives with respect to the unknown parameters beta 0 and beta 1, with respect to the parameters that we want to find. Since this is the function of two arguments, we take partial derivatives with respect to b0 and b1. So the first partial derivative, it's very simple. We have just the power function, right? So there is something to the power of 2, and there is a sum of n elements. So if you consider one element of this sum, one term of this sum, you will see that when we take the derivative of this expression with respect to b0, we will get 2 multiplied by this expression in brackets, and then we take the derivative of the inside functions, right? This is the chain rule, and then minus appears in front. So we have minus 2 for every term, for every I, we have minus 2 multiplied by the expression in brackets to the power of 1. Then we take this minus 2, we factor this out, and then we have minus 2 multiplied by this sum. Very simple thing. When we take the partial derivative with respect to b1 of this expression, we will get the following. So we will get minus 2 again in front of the summation sign, because we can factor out this minus 2 is going to be the common term for all the terms inside the sum. But one more thing here, when we take the derivative of inside function with respect to b1, there is going to be xi in front of the brackets. So therefore we have this, the brackets multiplied by xi, and everything is under the summation sign. Well, the solution of a minimization problem assumes that we must equal both partial derivatives to 0. And we need to solve them with respect to b0 and b1. Now, just to make it more precise, we need to denote that these are not just b0 and b1, but those are special b0 and b1, such that this expression is minimized. So therefore, we will change b0 and b1 with the following notation: beta 0 hat and beta 1 hat. This hat expression is already familiar to you from statistics. We denote the estimator with the help of this hat. So therefore, these are gonna be two random variables, and these two random variables are the solutions to these two equations. So we must solve these two equations. So first step, the logical step is to divide, let's take first and divide this by minus 2n. So minus 2 cancels. And when we divide this by n, and when we split this expression in under the summation sign into three terms, we will get this. So 1 over n multiplied by the sum of yi. What is this? Who can help? What is the first term? Come on, friends. This is very simple.
It's a mean of.
This is sample mean of y. Yes.
Yes.
What is the second term?
Sample mean of estimate.
But this is a number.
Intercepts.
This is a number. Beta 0 hat. I mean, once we have a data, it's gonna be a number, right? Based on the data. So therefore, it's just n beta 0 hat divided by n. It's just beta 0 hat. Here beta 1 hat goes out of the summation sign, and we have sample average of x. Here we are. So we can simplify this with the following way. Beta 0 hat minus beta 1 hat. Well, once again, once we collected the sample, beta 0 and beta 1 are numbers. So we treat them as numbers here. They are random variables before we collect the sample, but once we are working with the sample, those are just numbers. So therefore, beta 0 hat and beta 1 hat are going to be constants for every observation in our data. And this is the first expression. Well, if you take the second expression and do the same operation, we divide this by minus 2n, we will get something like this. We will get 1 over n multiplied by the summation of xi yi. Does this look familiar? We had this in our repetition here. See that this is something similar to this. So that's why I needed to show it to you. So here we have 1 over n multiplied by the sum of beta 0 hat xi. Look, you need to open the brackets here, right? So that's why we get it here. So beta 0 goes out of the summation sign, and we have the sample average of x. And here we have beta 1 multiplied by xi squared. Under the summation sign, beta 1 goes out of the summation sign because it's a number, and we have the sum of xi squared, which is divided by n, gives us the average of x squared. So finally, we have, so just to make notation a bit simpler, we have here the average of xi, so x multiplied by I, and then we have the sample average, or sample mean. Here we have just a sample mean of x, and here we have the sample mean of x squared. And these things are somehow related to that repetition slide with covariance and variance. So now we need to make them more visible, let's say. So let's take these two expressions, the first one, the second one, to the next slide. So we have a system of two equations, 1 and 2.
Can you go back to the previous slide? This means xy mean. So
Yeah.
it is a mean of x multiplied by mean
No,
of
no, no, no,
y,
no, no, no,
or
no. Completely
mean
different.
of
No, it's
the
x multiplied by y, and then we take the average.
okay.
Look, don't confuse these two things here. Look, this is the sum of these products, x and y, and then you divide this by n minus 1, and you have this like average. And this is the product of x bar and y bar separately. It's like this. It's like expectation of xi is not equal to the expectation of x multiplied to the expectation of y in general. Or like this.
They have like almost the same lines over them, so it's confusing.
So I did my best to distinguish them. So you have this is the one solid line here, and here, yeah, so it is not separated. That's why. But okay, so I clarify this. So this is the sample average of x multiplied by y. So you take x, you multiply this by y, then you sum over all the observations and divide by n.
Okay,
Here.
and the last regressor, like this one, it has also like the solid line. This.
Yes, so you take x, you square every x, and then you calculate the average. So it's not average squared, it's the average of x squared.
Okay, I get it. Thank you. So we first like
so
make an action.
I've made this to simplify the notation, just not to use all these summation signs. So basically you can always refer to the summation signs, and then later on the next slide you will have all the explanation of these things as well. But
Okay,
yes, thanks for asking, thanks for clarifying. But be careful with this. So where you have the square and where you have this line above. Okay, so we have these two equations and we need to solve them. So now it's very simple. We have two simple, very simple system of equations. So let's take the first and derive beta 0 hat. So we take beta 0 hat, move it to the right, and then we have y bar minus beta 1 hat x bar. Well, sample mean of y minus beta 1 hat multiplied by sample mean of x. Now we can take this beta 0 and plug this into the second. So this is the initial expression. Now instead of beta 0, we plug this expression. And this is the result. Now look what we can do. We can open the brackets here like this. X, look. So try to distinguish these two things. So this is the average of x, y, and this is the average of x multiplied by average of y. So those two are different things, like those expectation of xi and expectation of x multiplied by expectation of y. These are the sample counterparts. And you can guess that this is something similar to the covariance, to the sample covariance, but we need to a little bit to work on this a little bit more, because when it's sample, we need to divide by n minus 1. And here, when we factor out beta 1 hat, we have this. And this looks similar to sample variance. So now from here, we can easily derive beta 1 hat. So beta 1 hat is the following fraction. So we take the average of xy minus average of x multiplied by average of y divided by average of x squared minus average of x squared. So once again, don't confuse these two things. So this is average of x, and then we square this average. And this is x squared. We sum all this x squared, and then we calculate the average of them. Yeah, so here is an explanation. So this xy bar is calculated in the following way. X squared bar is calculated in this way. And x bar and y bar are familiar sample averages, sample means. So 4 elements, we need to calculate 4 elements in order to calculate this beta 1 hat. And once you have beta 1 hat, you can plug it here and calculate beta 0 hat. Yeah, we are done. We are done with the building of ordinary least squares estimators for beta 1 and beta 0 based on the sample. So now we can wrap up this. Just, to have some formal definition. So the OLS estimator, so the slope and the intercept are, this is the extended formula. So instead of xy bar, I put here the summation. And instead of x squared bar, I put here also this summation. Why I decided to do this? So now if you work on this a little bit more, we can see that this thing is equivalent to this thing. It's also possible. In the numerator, we have the part which is related to the sample covariance. Look, this is not sample covariance yet, but this is something similar to sample covariance. What we need to do is this to get the sample covariance. We just need to divide this by n minus 1. What do we have in the denominator? We have almost sample variance. But again, in order to make this sample variance, we need to divide this by n minus 1. So therefore, if for the fraction, we divide numerator and denominator by the same number, n minus 1, we will get the same fraction. That's why we can represent this beta 1 hat as the fraction of sample covariance x and y over sample variance of x. So all three formulas are totally fine and they work. Any of them works. Basically, depending on the situation, so whatever you want, you can calculate either with this or with this. And beta 0 hat is calculated in the same way as we have seen on the previous slide. So the repetition about sample variance and sample covariance was needed because just, to illustrate this equality, why we have this equals this, because both parts are related to the sample covariance. Well, here is the explanation. What is the sample covariance in this case? What is the sample variance in this case? And yes, so as we had in statistics, this is the way how you can calculate the estimates based on the sample. So this is just the mathematics. So I decided to put all the derivations, all the explanations, how did we get these formulas, how did we get these numbers. This is something similar to what we did in method of moments and maximum likelihood lectures and exercise sessions in statistics. So this is needed because we want to understand how, based on the sample, we can find what we are looking for. So now let's see how we can calculate these things based on the example. So remember that in the last lecture, we discussed the following linear regression model. We wanted to estimate the parameters beta 0 and beta 1 that relate test score to the student to teacher ratio. And of course, there is an error term, but we want to know these two things. Well, we want to estimate beta 0 and beta 1. We have calculated, I don't remember whether it was exercise session or lecture, but I guess in both of those activities, we have calculated the averages, test score, this, and average student to teacher ratio, this. And for every school district, we must build the following table. So if you want to calculate the beta 0 hat and beta 1 hat, we must build this table, calculate for every school district this and this deviation. It's kind of simple, right? So once we have this average, so let me demonstrate you for one particular district. So for example, for the first one, we take x, 2141, minus average. Average is 1964. And then we square this, and that's where we get this number. Well, of course, this is the difference in this table and the difference in my calculation is because of the rounding. I was calculating these results with the most precise numbers, but here, because of the rounding, we don't get the perfect match, of course. And this part is calculated in the similar way. We take x, 2141 minus average, 1964, and then we multiply this by y, 605, 55, minus y bar, 654, 16, here. And this is the result, minus 86. Here it's minus 85, 83. Again, because of the rounding. Maybe there is some harsh rounding, I don't know. And we calculate these values for every district. Why do we want this? Because then we want to sum them and divide by the sum of the other column. And that's actually why we are using software, because you can imagine that by hand to calculate all the things is almost impossible. Well, the sum of these elements, the sum of these products for all 420 districts is here. So we just sum over this column all the numbers. This is the result, minus 3,418.75. And the sum of the last column, this one, is here, 1,499.58. So basically we can divide one by the other. So let me show you, minus 418.75 divided by 1,499.58 in order to get this number, minus 220, almost 28. This is beta 1 hat when you divide this number by this number. Or we can do the following. Or we can calculate
to the table. Sorry. Yes, and just for the general understanding, xy minus min xy multiplied by y minus min y. How can we somehow call it? Just give it a name. What is it?
Well, this is the product of deviations of x and y from the respective sample averages. I would say it's too long to call it somehow.
So just when we minus regressor from its mean, I mean x minus mean x, it is
Well, this is a deviation of
of a
variable from
deviation.
its sample average, yes, or deviations from mean. You can call it like this. So this is the product of
So
deviations.
Yes, this one.
Product
Thank
of
you.
deviations, yes. This is the squared deviation, right? And this is the product of deviations of two variables.
So that's much better than just this.
But of course, when you say about deviations, if you want to be very precise, you must specify what kind of deviations. So deviations of variable from its average. So that's why it's too long.
And if it is long, it is more understandable in these words.
Yeah, okay.
Yes,
So we sum these products of deviations to get this number, and then we sum the squares of deviations of x to get this number. Then we can immediately divide one by the other in order to get beta 1 hat, or I decided to illustrate you how to apply the last formula here with the help of covariances. So this is the sample covariance of x and y. We divide the sum of deviations by the n minus 1, 419. We have this minus 816. This is the sample variance of x, this number divided by 420 minus 1. And then finally we can calculate beta 1 hat. As I said, either we can divide this by this directly, or we can divide covariance by sample variance, and we get the same, minus 228. You can see that the result is exactly the same as I calculated based on these two sums. Now this is beta 1 hat, and beta 0 hat can be calculated with the help of this formula, y bar minus beta 1 hat times x bar. We know this is y bar, this is x bar. We take them, plug here minus 228 to get 698.93. So overall, the estimated regression line, look, this is not the same as the population regression line, this is estimated regression line, looks like this. Test score hat, because this is the predicted part of test score, and this is not the exact test score, equals to beta 0 hat, 698.93, minus beta 1 hat 228 multiplied by the student to teacher ratio. So the subscript I means that we are talking about a particular school district. Yeah, so this is the result of our estimation. So we didn't know the parameters of the regression line. Now, with the help of data, we were able to estimate these two numbers, and that was our target. That's what we wanted to do. Now, if you look at the graphical representation of what we have found, so I decided to borrow this picture from the textbook instead of building this myself, but in the next week, in the exercise session, we will do this together with the help of Python. So we see that there is a scatter plot of data, and we have a line which has this estimated parameters 698.9 as the intercept. So if you extend this line here, there is going to be the intercept where the line intersects the vertical axis. But it is not reasonable because the data is bounded and between student to teacher ratio around 14 to 26. So everything that lays to the left of 14 cannot be explained with the help of this line. So therefore, the intercept, as we also discussed, does not have any economic interpretation. Minus 228 is a slope. This is how steep this line goes through the scatter plot. If you would have larger number, the line is going to be closer to the vertical, right? So if the number is small, it's going to be more horizontal. Yes?
Vlad is having some troubles with internet connection. He is begging to wait for him.
Okay, so I'm recording this lecture, so probably he can just watch this part with us.
No problem.
Okay, so this is the visual representation of our results. This is what we have estimated. Now, because we are only in the half, in the middle of the slide, so that's why I would better to continue. So now we need to discuss some terminology, some language that we are going to use for these OLS regressions and for our calculations. So first of all, we spoke that estimators of the unknown parameters are denoted as beta 0 hat and beta 1 hat respectively. So as in mathematical statistics, any estimator is represented with this hat above. What is very important, as usual, these two are random variables. Though those particular values, so these values 698.9 minus 228, those outcomes are based on this random sample. If we collect another sample of data, if we take other districts, we would have different numbers as the result. That's very important, and we will discuss this in the next lecture. So what are the consequences of the fact that these estimators are random variables? But you already know that because of randomness of these estimators, we must build confidence intervals, we must test statistical hypotheses, we must calculate what is the probability that our sample contradicts our beliefs. All we are doing in mathematical statistics last month, let's say, is the consequence of the randomness of these estimators. Well, this thing that we use as the result of estimation is called OLS regression line, sample regression line, or sample regression function. So the population version is called linear regression model. But once you put their sample thing, you always must be careful because we are talking about something which is estimated based on the data. Then, once you use this OLS regression line to calculate or to predict the value of y, we call this the predicted value of y. And we denote this also with the hat above, y hat. So look, there is a difference. Y is the actual observed value. Y hat is the predicted value. Y hat always belongs to the line. So y hat is always located on this line, on the blue line. Y is the vertical coordinate of this point. So for example, here, the actual y is 695. Y hat is here. So that's something like 660. So please mind this difference. That's why we put this hat above the outcome variable, because we want to stress the fact that we are not talking about the actual value. We are talking about the predicted value, which is based on our belief about the shape of this regression line. So this is the predicted value. And the difference between observed value and predicted value is called the residual, U hat. So the residual is the difference between, so that vertical distance between observed value and predicted value. And look, this is something similar to what we have discussed in the last lecture. Look, we spoke, let me go back here. We spoke about conditional expectation, which is represented by the population regression line. And we spoke about the error term, which is the difference between y and expected value of y. So now, everything that we have discussed here is about population. So if you want, this is our theoretical vision, how y can develop. So y can be divided into two parts. One part which is related to x, and another part which is not related to x. This is our belief, our theoretical model. We believe that this is true. And then we collect the data, and with the help of data, we get these. And these two things, y hat and u hat, are not the same as those things, because this is what we see from the data. This is our actual realization of the calculations. And this is also based on the sample. So please be careful with this. It is not the conditional expectation. Conditional expectation is our theoretical representation of the model. Error term is also theoretical part. It's not observed. This u hat and y hat, are obtained with the help of the data. You take another data, you get another u hat and y hat. But conditional expectation wouldn't change. The theoretical model is going to be the same. This is a very important thing. And I put everything in the table just, to show you this difference. So when we talk about population, so population consists of all objects. So this is something that we have discussed in mathematical statistics. I just want to draw your attention once again to this. Once we talk about sample, the sample contains n elements randomly chosen. Ideally, we want to have a random sample. Well, population parameters, beta 0 and beta 1, those are constants. As in mathematical statistics, like other parameters of the distribution, those are constants. The sample estimates, beta 0 and beta 1, are random variables. So these things are calculated based on sample, because the sample is random. Beta 0 and beta 1 are also random. Beta 0 and beta 1 heads. The error term U, represented by the sample counterpart, which is called residual U hat. Don't confuse these two things. Error term in population, residual in sample. Residual is, it's possible to calculate residual to get some number, and it is not possible to calculate the error term. This is just a theoretical part of our model. And then the population regression line, or conditional expectation of y given x, and this is a sample regression line, y hat equals to this thing. So this is very important thing to understand, and I hope after mathematical statistics you understand, at least to some extent, these two differences. So everything that we are talking about population, we are talking about something like mathematical modeling. So we mathematically, on paper, on the laptop, in our head, we model some process. We model the relationship between y and x. Once we practically collect numbers, calculate something, we are talking about samples. This is an important thing. Well, the example of predicted values and residuals. So I also extracted something from the table. And let's see. For example, we want to calculate the predicted value of y for the first district. What we need to do? We need to take that formula, beta 0 hat plus beta 1 hat multiplied by the student to teacher ratio. So we know that beta 0 hat is here, beta 1 hat is this one, and then we plug the value of student to teacher ratio, this 2141. We plug it here, and with the help of this, we are able to calculate the predicted value of y, or y hat, this 650. Look, this is the observed test score, 605.55. This is the predicted value, 650. As I said, predicted value belongs to the line. The actual value is somewhere in that cloud of points. Now we calculate the residual. The residual is calculated as the difference between observed value of y and predicted value of y, minus 44.58 here. And we do this for every observation in our sample in the same way. I guess this is very simple. This is simple logic. How to do this. Any questions?
No, but residual is like a static, yes?
Yes.
Okay, thank you.
Well, basically, it represents the effect of other factors other than x. But once again, theoretically, the error term represents it, and u hat, the residual, is able to it estimates the error term. It helps us to estimate the error term. Let's say we still don't know what is the true error term. We know nothing about population as usual. Well, now let's try to understand what we have discovered with this OLS regression line and what we can answer to the questions posed in the beginning of the last lecture. So if you remember, we came to the two questions, whether it is efficient for the government to reduce the number of students per teacher in order to improve the outcomes. That was one question, something related to the causal inference. And another question was, if you want to understand how well is going to be the performance of your kid once you send him to the school in a particular district, you can take the number of student to teacher ratio, plug it here, and predict some average test score for your kid. So first of all, we already know this, but I still put this on the slide. So this hat above the test score indicates that this is a predicted value based on the OLS line. So it's not an actual thing. So the estimated slope minus 228. What is the meaning? So we need to be careful with the interpretation of this number. So this means that when we compare two districts with class sizes that differ by one student per class, like 19 and 18, for example, the district with the larger class size has on average test scores that are lower by 228 points. So in short, if we increase number of students per teacher by 1 student per teacher, the average test score will reduce by 228 points. If we increase the number of students by 2, the average test score will go down by 456, and so on. So the logic is very simple. So this is the change in y when x changes by 1 unit. Well, as I said, the difference in student to teacher ratio by 2 students per class on average will be associated with the difference in test scores by 456. The negative slope, we are also interested in the sign of this coefficient. The negative slope means that once the number of students increases, the test score decreases. We have a negative relationship between these two variables. If we increase number of students per teacher by 1, test score goes down by 228. Now the question is, economically, practically, is this result large? Well, is this reduction in the test score or increase, if we decrease the number of students per teacher by 1, the test score will increase by 228. Is this large? Should we bother ourselves with this, with the class sizes? Well, we need to compare this with something. So don't look at 228 and don't tell that 228 is not a large number, therefore this is not a large effect, because it must be relative to something. So let's remind ourselves this table. We have seen this in the previous lecture. This is the summary statistics of two variables. What do we see? We see that student to teacher ratio, the range of this variable is between 17.3 and 20, so not the whole range, right? But the 10th percentile and 19th percentile are bounded between 7.3, 21.9. So there is something like 5 students per teacher difference, right? 7.3 plus 5 gives us 22.3. So less than 5 students. Therefore, 2 students per 1 teacher change is kind of large change relative to what we see in the data, right? So if we reduce the number of the number of students per teacher by 2 people, by 2 students, we can get from the median class into the 10th percentile class, or almost here, right? So from the average school, our school is gonna be the top school if we reduce the number of students per teacher by 2. Which means that the reduction of students per teacher by 2 is a large change relative to the data. It's really large. Now, we know that associated change in the test score is 456. if we reduce the number of students per teacher by 2, which is large compared to our sample, the test score will be reduced by 456. So again, if we had the median student to teacher ratio and median test score 654.5, so now let's reduce this 654.5 by 4 points, 456 points, right? It's gonna be 650, approximately 650. Where did we get? In 40th quantile, right? So the improvement of our school is not gonna be that large, which means that we are making a large effort relative to the observed data, but the outcome is gonna be very small, again, relative to what we see in the data. Because in order to make our school much better, we want to increase the test score. No, sorry, I was wrong. I was wrong with the explanation. If we reduce the number of students by 2, we will increase the test score by 4%, right? So it's not here, it should go here. So 654.5 plus 456 gives us almost this 60th percentile. But still, you see that the improvement is not that large. We are not falling into 90th percentile. So that's why, as I said, the difference of 2 students is large, but the associated predicted test score change is small. And as I said, we are making a very large effort with very modest or very small outcome. So practically, maybe we would say that it is not necessary to reduce or at least we can say that the such factor as a class size is not able to significantly improve the test scores of students. We need to search for some other characteristics. So we see that this, what we are talking about right now, it is not related to statistics. It is not related to mathematics. It is related to the real life understanding of the processes. We need to understand what exactly we have discovered and whether this effect is reasonable. And we can make some recommendation based on this. If you would ever want to work in data analysis, you really need to have this skill. It's not only about calculating numbers and showing these numbers. You also need to do some storytelling. You need to be able to interpret the numbers, and that's what we will try to do in the next exercise session. So we will see some OLS regression models, and we will try to discuss what exactly is there. Are there any questions about this interpretation?
So if we made a change of two students S, so if Esther was 17.3, but our change would be like to the 90th percentile, it would be a good
No. Yes, if you would change this by like 10 or 20 points, then yes. But unfortunately, data shows that the reduction of students per teacher by 2 will at most change the student to teacher ratio by 4.5 points, which is very small result.
Okay.
If the slope is going to be like -10, then yes. Then you can immediately improve the test score by 20%, by 20 points, sorry, from 654 to 674, and that's gonna put you somewhere here, right, between 75 and 90 percentile. So this is a significant improvement. But unfortunately, data shows that it's not true. There is only 2.28 slope in the model. Okay, so how do we do this prediction? So basically, we already made it, but let me show you once again. If we have this estimated regression line, using this regression line, we now can predict the average test score if there is some student to teacher ratio given. It's a very simple exercise. If a district has 20 students per teacher, the predicted test score is here, 698.9 minus 228 multiplied by 20. Instead of student to teacher ratio, you put 20, and then you calculate this 653.3. So on average, we expect that a district with 20 students per teacher will have that much of a test score. Nothing difficult, like the exercise for the second grade of the school. You always must remember that this is not exact prediction. You never know what will be the exact value. Why? Because there are other factors that affect a district performance, that affects this test score. So therefore, please always be careful with the formulation. We are talking about average. We are talking about the test score on average. Yeah, so this gives a prediction of a test score when other factors are excluded. Only student to teacher ratio, but of course, in reality, the result is going to be different. Well, and the last part of today's lecture is related to the following question. So now we have discovered several things. So first thing that we are able to guess those values of beta 0 and beta 1. This is just mathematics. Second thing that once we established the OLS regression line, and once we make some predictions, we see that, well, this prediction may work not well. Now we want to understand how well this prediction is. So when we use this OLS regression line in order to predict the value of test score, how reliable is our prediction? How close we can expect it to be from the real value? And this is called measure of fit, or measures of fit. So how do we measure the fit of OLS regression line to the data? Well, the intuitive question is how well this regression is able to explain the variation in the dependent variable. So if the dependent variable changes, can the regressor X explain this change well, or it fails to explain this change? That's the question. So we can write the dependent variable y as the sum of two parts, y hat and u hat. This is something similar to the population model where there is expected value and error. But now we are talking about the prediction. So what is calculated based on the sample.
May I interrupt? Why didn't we like compare if the change is important, like with the hypothesis testing? Is there any way?
Wait, yes. Don't confuse these two things. We are talking about economic significance, and we're also talking about statistical significance. So
Yes.
our discussion about statistical significance will be in the next lecture. You're heading in front of the lectures with your thoughts, which is nice. So this is very reasonable question. But look, with the help of hypothesis test, we are able to test whether the value of beta, the calculated value of beta, is reliable and whether it significantly differs from zero, or kind of saying simpler, whether this effect is present at all, right? So, or maybe we just randomly calculated minus 228, but there is no effect of student to teacher ratio on the test score. It's also possible, right? In the population, there is no effect. That's going to be our null hypothesis once we start our discussion about significance, statistical significance, and hypothesis tests. But economic significance is something different, because even if statistical significance gives you that this parameter, this estimate, is statistically significant at a given significance level, the value itself can be very small and the effect is going to be, well, nothing at all. And that's what we have discussed there. So we wanted to understand whether our question at hand, right? So whether we are investigating the effect of class size on the student's performance, whether this question matters at all. I mean, practically. Or maybe we are just trying to improve the test score with the wrong lever, with the wrong factor.
Okay, I see.
This is clear. So just try to
Yes,
kind of
kind of.
separate these two concepts: economic significance and statistical significance. Economic significance is always about benefits and costs. So how much you need to invest in order to get some result. And that's what we see. You need to invest a lot. You need to shift your district from median to the 10th percentile in reducing the number of students per teacher by 2. But as the benefit, it will shift your district from median to 60th percentile, which is incomparable, right? So you need to make your school one of the best in terms of class sizes. But on the other hand, your school will move slightly in terms of the test score. That's economic significance. And this is related somehow to the question of the causality. So if I change x, how much y is going to be changed? But now we are talking about predictions. Now we are talking about predictions because sometimes predictions are also needed to be done. So instead of some normative things, instead of some causality questions, we want to just predict something. Well, this is a particular example about class sizes and test scores. So we will be talking about some other examples in your home assignments, in your exercise sessions. And you will see that not all of them such simple. So sometimes the questions of prediction are very, very important things. And we use the same techniques for making some economic forecasting or forecasting on the financial markets. So back to this discussion. So we want to know how well is our model in terms of prediction, how close the prediction is going to be to the actual value. Because if it is not able to predict kind of sharply, so maybe the quality of our model is not that good. So we divide y into two parts: OLS regression part, predicted value of y, and the residual. Now, intuitively, y hat is the part of y which is explained with the help of xi. So this is what we are able to explain with the help of our model. And y hat is the part which is unexplained by x. I don't know why y hat u hat, sorry, disappeared, but this is there must be this u hat here. This is the residual. So we want to compare the sample variance of y hat with the sample variance of y. Because sample variance of y captures the variation of y. And this variation is divided into two parts, variation of y hat and variation of u hat. And this also must remind you of ANOVA, which we also used for the same purpose. We divided our outcome variable into two parts. One part is the variation because of the factor, another part is the variation because of the error. And we compared those variances. So again, I hope you see some similarities. Well, so if we have this decomposition of y, we can decompose the variance of y also into two parts. So we can calculate total sum of squares, and this total sum of squares is going to be divided into the regression sum of squares. So now it's not within and between, don't confuse these two things. The concept is the same, but the names are slightly different. This is the sum of squares for the regression, this part, and sum of squares for the residuals, this part, or residual sum of squares, or error sum of squares. So there are many different terms, so we will stick to the same notation as in statistics course. Remember ANOVA, we did the same.
Which of them is within? Which of them is
No. It's
No?
not within and between. Don't confuse these two things, please. It's like the concept is the same. We want to split the variation into two parts, but within and between it was about ANOVA because we had different groups of or different samples. So this between is the variance which explains which captures the variation because of different groups. The analog of this between, the analog, but not, don't call this within and between. The analog is this regression sum of squares. So the part which is explained with the changes of x. And this is the part which is unexplained with the help of our model. That's a similarity, right? So the part of variation which is explained because of different samples, and the part which is random part. The same is here. So the total sum of squares must be familiar. We calculate the squared deviations of y and then sum them. The explained or regression sum of squares is calculated as the squared deviations of y hat from y bar. So this is important. It's not y, it's y hat. The sum of squared residuals is calculated as, well, this is the residual, y minus y hat squared. And once we know that this is a residual, we just take u hat squared. And now, if you remember, in ANOVA, we compare this part with this part. But instead of doing this, we calculate the measure which is called regression R squared. So regression R squared is the fraction of this part explained sum of squares or regression sum of squares by the total sum of squares. And this is the fraction of the sample variance of y, which is explained by x. So it's not the same. It's not a statistical test. No, it's something different. It gives us this measure, R squared. It is not related to any hypothesis test. Don't confuse these two things. So I just want to show you that there is some similarity with ANOVA, because this is the same approach. We want to decompose the variation into two parts. But now this approach moves us to the other direction. So with the help of this approach, we calculate how much of the variation in y is explained with the help of our regression model. we compare this part with this part. So in this case, we move away from ANOVA. Still ANOVA will appear once, but not in this part. So another way to calculate R squared, well, if this regression sum of squares is going to be represented as the difference of total sum of squares and residual sum of squares, just try to imagine SSReg is SS tot minus SS res, right? So residual sum of squares. Then we plug it here, divide by terms by SS total, and then we will get this 1 minus this number. Well, what is special about this R squared? How can we interpret this? Well, the interpretation is here, fraction of sample variance of y explained by x. Why do we want to calculate this R squared? It is nice in terms of its features. R squared takes values between, is there any ideas? Which values R squared can take on?
Positive.
Okay, I agree, positive. Is there any boundary from above? Maybe looking at this. Maybe looking at this fraction. Is there any maximum possible?
1.
It's 1. Yes, it's 1. It should be from 0 to 1. Well, and we must remember this. This is something similar to the correlation coefficient, but not exactly. There is some relationship, and we will talk about this, but again, so this is just a similarity. Well, if R squared is close to 1, this indicates that regression sum of squares is large related to the total sum of squares. What does this indicate? It indicates that the regressor is good at predicting y, right? So our model performs good and we are able to predict y more or less good. If R squared is close to 0, this indicates the regressor is not very good at predicting y. So that's very simple interpretation of R squared. You calculate R squared, if it's close to 0, well, your model is not able to predict y in a precise way. If it's close to 1, your model perfectly fits. We will discuss about whether it's necessary to inflate R squared or not. I mean, so the current research, for example, is totally fine with R squared something like 0.05, 0.02, because sometimes you don't want this R squared to be large. There are different, let's say, tasks. Don't always look at R squared, but sometimes you want it to be large, sometimes not. We will discuss. Well, let me skip this part. We will discuss this on the exercise session, how to calculate R squared based on our sample. Don't worry, so I will skip this part. This is just an example of the calculation of R squared with the help of our data. Well, basically R squared for our model is 5.1%. It's very close to 0, right? So the student to teacher ratio is able to explain only 5.1% of variation in the test score. So which means that the test score in 95% of the test score, in 95% of cases, it changes because of some other factors, not because of the class size, right? So the class size is not that important factor, relatively not important factor, which influences the test score. So there is a second evidence which shows that test score is not that reasonable.
Can you say that this is a significance interval?
No, not at all. It has nothing to do with significance. No. It is because, look, significance is about probability. It's not about probability. We haven't told about probability anything today. So we will start kind of introducing probability framework in the next lecture about hypothesis tests and all these things. So now we are doing only algebra. No, it's like, it's like, well, the test score can depend on different factors. Income of parents, how smart is the student, how good are the teachers, how well is the school financed, and so on. So we have discussed these things with you. So many different factors can influence the test score of this particular school. And out of all these factors, student to teacher ratio, like if you take the influence of all the factors as 100%, then student to teacher ratio, the class size, influences the test score only with 5.1%. So it's not about probability. It's not about confidence level. It's about like the whole set of factors that are able to influence the test score. And out of this whole set, student to teacher ratio explains only 5.1%. That would be more, let's say, precise to explain this. Well, okay, so we are running out of time, so let me skip this part. We will talk about this in the next class about the regression error, standard error of the regression. So don't worry. Well, now some concluding remarks. So what we have studied. We know how to estimate the unknown parameters of the linear regression model, which is nice and a good development of our knowledge. So we studied partially how to assess the goodness of fit of the model. Well, what was very important, and thanks for raising this question, that the estimates are random variables, and we need to know their sampling distributions. Always. When you're working with something random, you must ask about the distribution. And we want to conduct some statistical hypotheses about the population parameters beta 0 and beta 1. So that's what we will do in the next lecture in 2 weeks. And one last thing. On Monday, starting from the midnight till the midnight 23:59, you will have a short quiz on this lecture. So something similar to the previous quiz, some questions. What does this mean? Is it true that something is something? Predict the value of a test score if student to teacher ratio equals to this. Something very similar to the previous quiz that we had. Okay, that's all for today. Any questions?
Yes.
So the quiz will be only for 1 day, yes?
Yeah. So it will be open on Monday 00 and it will end on 23:59. So you're free for the weekend. I don't want to give you some additional work for the weekend.
Thank you very much.
Yes. Oh, and when will we have a midterm on econometrics?
Later, maybe in the middle of April, because we just started econometrics. We need to get some necessary materials. So we have, as planned, we have 9 lectures of econometrics. This is the 3rd one. So therefore you can count on like after 5th, maybe 6th lecture, something like a midterm.
And also we wanted to know if we have exam or like just a pass, not passed on our.
Nice question. I don't know. I will clarify this.
Okay.
For me, it doesn't matter. I still have the same requirements. For you, it matters, of course, either to get 50% or 91%.
Okay.
I will clarify and let you know.
Okay, that's all.
Anything else? Any other questions? Great. So you have plenty of things to do, right? From statistics, from econometrics. So please don't put this till the end of next week, and let me know if there are some troubles, some questions. Otherwise, see you on Thursday.
Thank you for the class.
Bye
Bye
bye.
bye.